Deep Dive is an ongoing Gamasutra series with the goal of shedding light on specific design, art, or technical features within a video game, in order to show how seemingly simple, fundamental design decisions are not really that simple at all. Check out earlier installments, including Doing a Real Human Scalper, The Audio of Insight, and the challenge of creating a VRFPS in Space Pirate Trainer. My name is Owen Mc Carthy. I am a principal programmer for Frontier. I studied computer science and theoretical physics at university and did an MSc in game development at the University of Hull. Before joining Frontier 9 years ago, I usually end up working on something physics or simulation related. I worked on reactive water simulation and the physics in Kinectimals. I have worked with some really fun signal processing on Kinect Disneyland adventures, so we could map the player's movements to their in-game avatar with as little jitter and lag as possible. I then worked on building destruction and ragdolls for Screamride. Most recently, I worked on the crowd simulation in Planet Coaster. I really love building believable worlds, and game development is definitely the place to be to make that happen. For Planet Coaster, we wanted to make the best ever crowds in the sim genre. That meant huge numbers, few intersections, and novel approaches to sound, art and animation. In Planet Coaster's voxel-based sandbox, we wanted to simulate 10,000 park guests at once, and we wanted them to look like a real crowd. We also wanted them to be able to handle curved paths, which had proven a challenging task in crowd simulations from our previous games, but something we considered essential to Planet Coaster. Traditional pathfinding methods are not suitable for simulating huge numbers of characters in real time. Usually each agent would compute a path separately and then move along it. But this tends to be very expensive and does not scale well. Trying to add collision avoidance afterward becomes a mess of edge case handling. We use potential flow fields to simulate the crowd in Planet Coaster. We have parallelized the computation across CPU cores and frame boundaries to minimize impact on the frame rate. We also had to implement non-standard approaches for sound, art and animation systems. At the beginning of Planet Coaster's development, we knew we wanted to move the genre forward. One thing I was particularly invested in was bringing the atmosphere of a real crowd into our virtual world, and in making each park guest aware of their surroundings. I wanted to capture little moments like walking by an entertainer, doing silly things and seeing other guests watching and reacting. We reviewed the state of the art in relation to crowd simulation and navigation. That involved reading lots of research papers, studying techniques and analyzing the feasibility of each one, taking into account scalability, memory usage and CPU performance. We watched hours of footage of crowds moving around theme parks, and we captured footage of our own. 10,000 guests was the number that we targeted right from the beginning, and simulating each one individually seemed like a real challenge, so we focused on a smaller number. There are fewer goals in a theme park than guests. Rides, coasters, shops and facilities are all goals. This was where the technique of using flow potential fields became very appealing. Instead of computing a path from A to B for each person, a path from each goal to all possible positions is computed. The question was, can we simulate a few hundred goals in a flow simulation more cheaply than we could simulate 10,000 individual paths with something like the algorithm? We had prototypes of several different Planet Coaster technologies in development in parallel. We started development on a voxel-based landscape system, and we really wanted to break out of the traditional grid-based path system. Ultimately, the crowd system would need to be integrated with the voxel, terrain and path systems. But early in development, they were still unknowns, so the crowd system had to be robust enough to fit whatever these systems became. It was easier to develop this crowd prototype in isolation, but to be constantly aware of making it amenable to changes elsewhere. The crowd system was much more robust. As a result of this separation, requests for changes to the path system throughout development were little to no work to integrate with the crowd system. The crowd system just deals with shapes to add to its flow simulation, and it does not really care about the source of them. For example, during the first alpha, we could only have straight elevating paths. It would have been possible to exploit this fact for ease of implementation of overlapping paths. But later on, the designers wanted to have curving elevating paths, and they implemented them. They just worked fine with the crowd system, and became a feature for the second alpha release. I started creating a flow simulation on a flat grid-based system to begin with. But flow fields for each goal do not interact with each other directly. The interaction happens indirectly by resolving around a density and velocity field generated from all of the guests in the simulation. These flow fields exhibit many of the properties found in high-density real crowds. They interact with each other and flow around each other and form emergent structures like lanes and congestion, and they allow agents to flow around congestion. I think the best way to imagine how a flow simulation works is to picture a table with raised edges. Inside this table is your park and its network of paths, and each goal point has a different water tap connected to it. Scattered across the table are marbles, which will flow with the water. When you want to solve a particular goal, you turn on that tap and watch the water flow through the path network, and push the marbles around. Each tap can only move its set of marbles, and other taps, marbles, are frozen in place as obstacles. We record the velocity of the water every time it flows into a new cell on the table. Once the entire table is filled with water, you have effectively solved the flow field away from that goal. Now, you can reverse the direction of the flow. Pick any point on that table, and inspect the velocity of it, and it is now directing the particle to the goal. You can now put as many agents as you like anywhere on that grid, and you'll instantly know which way they need to move to get to that goal. You can keep this velocity field in memory until a new one is computed, and continue to flow agents on the existing data. Figure 1. In essence, you are propagating a wave through a grid and recording the velocity of a wave the first time it enters every cell. When this prototype was up and running with really simple debug, rendering on the spheres for each guest, we needed to test the CPU on the memory performance to see if this technique was viable at the scale we were aiming for. We built a stress test map with the same dimensions as the target map size. This map had a few hundred goals and about 10,000 agents on it. While memory usage was a little bit over budget, we were confident that eventually we could drastically reduce it. The CPU usage was heavy, but the system was single-threaded at this point. We already had a vision to parallelize the simulation so that it would not be a limiting factor. Figure 2. It was now time to get rid of the debug rendering. The art team had already started taking the concept art and turning it into models we could use. Each guest was planned to have interchangeable body parts with lots of texture and skintone variation. We have a great animation team at Frontier, with lots of experience making quality animations. but due to the number of guests, we needed to limit the animation blending that could take place. Front-facing characters in game animations typically use both space blending with many layered animations, which makes it expensive to compute the nonlinear final bone transformation. Instead of this, we'll start the bone transformations from aren frame, not keyframe, of the animation in memory, and use a simple interpolation of the nearest 2 frames.